Hello guys, welcome to the second part of this lecture. On the first part we talked about the Fermi function, which is the probability of occupation of electrons, and we plotted this function as a function of energy for an intrinsic semiconductor at 0K and 300K, so for undoped semiconductors. Now we're going to talk about how the Fermi function looks like for doped semiconductors, both N-type and P-type semiconductors, and relate this to the physical properties. So each state can either be occupied by an electron or it can be empty. A given state can either have an electron or it can be empty. So if we talk about the band structure, E is a function of K. Again, for a direct band gap semiconductor, just as an example, of course, you'd have similar things for an indirect band gap semiconductor. So you have the states, right, in the conduction band and the valence band, and these states can be occupied or not. You could look at the band diagram as well, right? But if the state is occupied, it has an electron. Typically, I will represent this by a full circle. And if the state is empty, it is not occupied by an electron. So I'll represent this by an empty circle, right? And at 0K, we saw that, all of the states at the conduction band were empty and all of the states in the valence band were filled. As you raise the temperature, some electrons are able to transition up to the conduction band, leaving holes behind. So remember that the empty states correspond to holes only if they are in the valence band, right? These empty states in the conduction band are just empty states. They cannot be used to conduct electricity. Only electrons in the conduction band and holes in the valence band can be used to conduct electricity. So these are some of the concepts that we saw. Since a hole is a vacant state, the probability of there being a hole at energy level E is equal to 1 minus the probability of occupation for electrons, or 1 minus the Fermi function f of E. Okay, so the probability of having a hole here, let me draw this again, having a hole here is given by this, right? We could define FH of E. This is not usual, okay? So the probability of occupation by holes, which is actually the probability that the state is empty, is 1 minus F of E, because the state can be either occupied or unoccupied. There's no third option. So if there is not an electron, then there must be a hole, right? So 1 minus the probability of there being an electron is the probability of the state being vacant, being empty, being occupied by a hole. So for any energy within the valence band, the probability of finding a hole is the distance between the f of E curve and the f of V equals to one line, dash blue. So let's go back to the depiction and look at this for an instant. So what we're saying here is that, let's say we're talking about intrinsic semiconductor at 300K. The red curve here is f of E. Okay, so it's the probability of occupation for electrons. The probability of occupations for holes is 1 minus this function. So it is actually the dashed curve here in blue corresponds to f of V equal to 1, right? Along this line here, f of V is equal to 1. So the distance between this dashed line and the red line is the probability of occupation for holes, which is 1 minus f of E. Okay, so right here at the edge of the valence band, right here, you have this probability. Let's try to zoom in here, okay, to see what we're talking about. So this distance here, right, between the dashed blue line and the red curve right here, this small gap or this small distance here is the probability that the state, the respective state with this energy is empty, because the complementary probability, which is illustrated in green, which goes from 0 to the red curve, is the probability that the state is filled by an electron. So as a consequence, the complement, or 1 minus f of e, which is this part right here, is the probability that the state is empty. So it's the probability that there is a hole in here. So if for a given energy, below the edge of the valence band, let's say that f of e, the probability of occupation, is 0.98, so a little below 1, then the probability that the corresponding state at this given energy is occupied with an electron is 98%. And the probability that the state is occupied by a hole or is not occupied by an electron, as a consequence, is 1 minus this, so therefore it's 0.02 or 2%. Okay, so there's 98% chance that it's occupied by an electron. Therefore, there's a 2% chance that it's not. Therefore, if it's not occupied by an electron, it's occupied by a hole. It's empty, or it's a vacant state. Now, a few more things. The probability of there being electrons in the conduction band and holes in the valence band decreases with Eg, okay, with the gap energy. So it will be very low for dielectrics. For small band gap semiconductors, it tends to get larger. Again, if we go back to the curve, so what would happen is that if this Eg, this gap, was larger, then the edge of the conduction band would be, up here perhaps, way up here, if it was larger like this instead of being what it is. So the edge of the conduction band, the new value of EC, would be this, and for a different material, for a different semiconductor, and the value of EV, the band edge for the valence band, would be this. And as you can see here, right, you have a smaller, this distance here between the red curve and 0 is smaller than it is right here. So there's a smaller chance of having an electron here, smaller probability. The same thing will happen for holes here. This distance here is smaller than this distance right here, right? Therefore, here you'll have a smaller probability of having holes than here. So as you increase the gap in energy, larger band gap semiconductors, and going further into dielectrics and so on, as the gap gets larger, the probability of having electrons in the conduction band will be smaller because this distance is smaller, and the probability of having holes in the valence band will be smaller because this distance again is smaller than this distance right here. If you increase even more, this will be more pronounced. So this gives us an indicative of why dielectrics or large band gap semiconductors have less carriers, less electrons, and less holes than smaller band gap semiconductors. Now, also, the probability of there being electrons in the conduction band and holes in the valence band increases with temperature. So you can check this by plotting the Fermi function. And if you plot this, if you plot this for different values of T and you increase the temperature, you can do this in MATLAB, for example, you will find that as the temperature increases, the curve becomes smoother and smoother. So let's say for a higher temperature than 300 K, this curve might look like something like this. I'm extrapolating a little bit here, but it would be even smoother. So therefore you see that the probability of having electrons here for the purple curve is larger because this distance here is larger than for the red curve, right? This is what happened when you increase temperature. The same thing goes for the holes here, right? The probability in the purple curve, you have a larger probability of finding an empty state here than in the red curve because the distance here is larger. And this can be explained physically because once you increase the temperature, you're supplying more energies for the electrons in the valence band to rise up to the conduction band. So you find more electrons here and more empty states here because the electrons moved up in energy. In order to make useful devices using PN junctions and other types of junctions, we need to dope the semiconductor. So the process of doping alters the properties of the material. It alters the conductivity, the carrier concentration for electrons or holes. And in practice, this is achieved through two basic processes, which are ion implantation or ion diffusion. These dopants are introduced in a relatively small amount, usually of the order of 10 to the 12th to 10 to the 17th, or perhaps even 10 to the 20th impurity ions per cubic centimeter. So you have this amount of ions in 1 cubic centimeter of a material. And these ions are going to be responsible for providing the additional electrons or holes depending on the dopant. So doping can be achieved with acceptor elements or donor elements. So for example, for silicon, you have boron and aluminium as examples of acceptor elements, which usually in this case have 3 electrons in the valence shell. Also for silicon, examples of donor elements are phosphorus and arsenic, which have 5 electrons in the valence shell. An N-type semiconductor is doped with donor impurities, as we said, and the donor elements introduce electrons at states close to the border of the conduction band. So let's say that we have a donor element. How is it going to behave, right? Well, for an intrinsic semiconductor, such as silicon, you have the valence electrons in the valence shell, and these are shared by covalent bonds with other silicon atoms. So for example, this silicon atom shares these 2 electrons with this silicon atom, and so on. This silicon atom shares these 2 electrons with this silicon atom. So let's say that originally the electrons related to this atom are the ones that are highlighted in red here. Okay, so these 4, since silicon has 4 valence electrons. Well, if you dope the material, you substitute some atoms in the crystalline structure by the impurities that are added. So for example, if we want to obtain an N-type semiconductor, we're going to dope it with donor impurity, such as phosphorus, which instead of having 4 valence electrons, in this case has 5, right? So it has these 4 electrons, which are still shared in the covalent bonds, but this extra electron provided by the donor impurity, the phosphorus atom in this case, is not shared in any covalent bond. So in fact, this electron is related to a new level that is introduced in the band structure. So, if the original material has the conduction band and the valence band, now we're talking about the band diagram. So we're looking at energy, and you have the original bands of the semiconductor. You might ask, how is this band diagram going to be altered once you introduce a donor impurity? Well, the donor impurity, such as phosphorus, is going to introduce an extra level, which is going to be occupied by an extra electron, which is the electron we just mentioned, this one right here. But it's going to introduce an extra level, which is going to be occupied by an electron. And this extra level, the important part is that it's going to be close to the conduction band in such a way that with a very small amount of energy, this electron can transition up in energy into the conduction band. So you have additional electrons in the conduction band because of this. Okay, so this is the picture. The donor impurity will have an additional electron associated with a state with an energy level that is close to the conduction band, and therefore the electron can easily transition into the conduction band of the doped material. So with the increased number of electrons at the conduction band, and this number is going to be exactly equal to the amount of donor impurities that you have doped the material with, so 10 to the 12th to 10 to the 20th electrons, what will happen is that the Fermi function and the Fermi level will shift toward the conduction band, okay? Because you have all of these extra electrons, so 10 to the 12th to 10 to the 20th electrons in the conduction band. What you'll see is that the Fermi level, right, instead of being right here at the center, as is the case for intrinsic undoped materials, it will shift up, reflecting the fact that now you have more electrons here. So the probability of finding electrons here has to have increased, right, by this amount. So therefore, the Fermi level rises and is now closer to the conduction band, and you have a higher probability of occupation of electrons in the conduction band. Also, since you have more electrons in the conduction band, some electrons are going to recombine or transition in energy down to the valence band. So a few of these electrons will make the downward transition in energy and occupy some of the free states here. And therefore, the whole concentration is going to actually decrease. So you get more electrons, and as a consequence, less holes in an N-type semiconductor. And this is reflected by the fact that if you compare, this gap right here, which, as we've discussed previously, is associated with the probability of occupation of holes, it's going to be smaller than for an undoped material. Because of the free electrons introduced, there's a higher probability of finding electrons in the conduction band, but the overall shape of the Fermi function does not change. So this function in red here, the Fermi function, has the same shape as it did for an intrinsic material. It's only shifted up towards the conduction band. And the more you dope the semiconductor, the higher the Fermi level is going to be towards the conduction band. A p-type semiconductor, on the other hand, is doped with acceptor impurities. So instead of the original silicon material, you have a material where some of the atoms are substituted by acceptor impurities, such as boron in silicon. So in this case, the acceptor impurity, boron, has 3 valence electrons. Okay, so it will share all of these electrons with adjacent atoms. So these 2 electrons are shared between the boron atom and the silicon atom right here. These 2 are shared between these 2 atoms, and these 2 electrons are shared between these 2 atoms. But it's lacking 1 electron that cannot be shared with any other silicon atom. So it actually is going to have a lack of an electron or a hole. Okay, this is 1 electron missing, so it's actually a hole introduced by the acceptor impurity, the boron atom. And these holes are vacant states that are introduced close to the border of the valence band. So if we're talking about the band diagram, for the original material you had the conduction band, the valence band. Now with the doping, the acceptor impurity has introduced an empty level, an empty energy level, or an empty state with an energy level that is right here. And this empty level means that an electron in the band edge, the valence band edge, can transition up to this level. So the electron in the silicon lattice is going to transition into this level introduced by the impurity. Okay, leaving behind an additional hole, because the electron has moved up to that level, it's going to leave an empty state, which is a hole in the valence band. So in this way, acceptor impurities cause the generation of more holes in the valence band, the addition of holes to the valence band. Okay, with the increased number of holes at the valence band, the Fermi function and the Fermi level shift downwards toward the valence band. So instead of shifting up, now from the center position it shifts down, right, for a p-type semiconductor with acceptor impurities. Because of what we've just discussed, the Fermi level will shift down. Why does it shift down? Well, you have more holes that are introduced by the acceptor dopants. So since you have more holes, you have a larger probability of having holes here, and therefore this probability, the probability of occupation of holes, has to be larger than for an intrinsic material. This is what causes the whole Fermi function and level to shift down. Since you have more holes here, some electrons that are in the conduction band can now move down to occupy all of these extra holes that you have, and therefore the probability of finding electrons is decreased with respect to an intrinsic material. So in a p-type semiconductor, you have more holes and less electrons than you would have in an intrinsic type material. So because of the additional holes introduced, there's a higher probability of finding holes in the valence band. So you have extra holes and fewer electrons in this case. Okay guys, so this was it for this lecture. On our next lecture, we're gonna keep talking about Fermi functions. So thanks very much for your attention, and I'll see you around.